We have taken the classic multi-layer perceptrons or MLPs for granted and built so many architectures around it. MLPs are part and parcel of every single large language model or foundation model that we see today, such as ChatGPT, DALLE, YOLO, LLAMA, Clip, Imagen, or even Stable Diffusion for image or video generation. What if I now tell you that we have a new competitor for the very MLPs? There's a new paper in town called the Kolmogorov-Arnold Network, or KAN in short, which challenges the MLPs. If the solution they are proposing truly scales, then we can have the next generation of neural networks, which will take us yet another step closer to artificial general intelligence. While the MLPs comprise of activation functions such as ReLU, sigmoid, tanh, leaky ReLU, SeLU, ALU, KAN proposes that we learn these activation functions. So how does KAN do it? What's the mathematics behind it? And how is it implemented? How do you even train these networks? Let's find out in this video. So the paper starts with showing the difference between multi-layer perceptrons and Kolmogorov-Arnold network. And the underlying theorem for MLPs is the universal approximation theorem. But for KAN networks is obviously Kolmogorov-Arnold representation theorem. And how we represent MLPs is by now very clear that we have activation function and we have the weights and the input X and a bias term B. The MLPs are represented by this familiar network where we have fixed activation functions, which are these nodes. We have these edges, which is flowing between the nodes, which is the learnable weights on these edges. And when it comes to KANs, we have the summation operation that's happening on the nodes. So each of these black dots represents the sum operation. And we have these learnable activation functions on the edges. We can see that the shape of these functions is all different because they are learned on the go during training, and we really cannot determine what the eventual shape of these functions will be. In terms of the formula, we know that we have the nonlinear fixed activations and we have linear weights, which are learned during the training. But when it comes to KANs, we have nonlinear learnable functions, and all these functions over here get updated during the training process and they are learned, and we have an eventual network which has the combination or summation of all these learned functions. So in order to understand how the KAN works, we need to look into how the basic polynomials can be combined in order to build complex polynomials. So what we have got here is two polynomial functions, y equal to x squared and y equal to x cubed, that are wiggling up and down. Basically, the curve in blue is the y equal to x squared curve. That's more of a U-shaped curve. And the curve in yellow is the function y equal to x cubed, which is more of a S-shaped curve that's been turned by 90 degrees. Let's take a simple binary classification problem where one of the classes is represented by these red dots and one of the classes is represented by the blue dots, and we want to find the boundary line between the two. So instead of using a high degree polynomial, which is y equal to x cubed, that is represented by this yellow curve, we could use a combination of y equal to x squared curve and then give a condition that, whenever the x value is greater than 0, we'll have to use y equal to minus x squared. So that'll be a curve something like this, because now the blue curve is the negative. But when the x value is negative, we'll be using the same curve for y equal to x squared. So now we have a combination of two x squared functions which serves the purpose that's equivalent to an x cubed function. Let's take a slightly more sophisticated toy example where we know that the data is generated with a known equation that's given here. So we have four variables, x1, x2, x3, and x4 at the input, and we have the y at the output. So if we are designing a KAN network, then we'll have to go about this problem by having three layers, assuming that in the first layer when we are doing the training, all the x squared functions will be learned. And in the next layer, all the sinusoids will be learned. And in the last layer, we'll have all the exponents to be learned. And in the input, we have, of course, the 4 variables. And at the output, we have our output y. So we initialize these randomly. And then after the training with the data that's generated with this equation, we will notice that all these functions have converged to x squared function, sinusoid, and exponential function. But the problem in real life is that we actually do not know this equation. We don't know the equation that governs the data that we have on hand. So how do we go about that? So the answer lies with B-splines. So the fundamental idea of B-splines is that any given function can be represented as a combination of simpler basis functions or curves. For example, let's take this curve as an example. This curve, in turn, can be represented as a combination of simpler basis functions. Let's say we want to break it down in these points. And then let's represent it with a combination of 2 basis functions. Let's say the basis functions are represented by b. And there can be I number of basis functions that can take the input, and a combination of all of these basis functions, which is controlled by control points I, leads to our spline, which is a B-spline basically. So the basis functions will represent the curve like this, and they join at this point called knots, and the next basis function will go like this. And again, there's a knot here. So these points where these 2 points these 2 curves or functions combine is called the knots. One of the drawbacks of breaking down a given continuous function into these smaller representations is that there can be discontinuity when we at these knots. For example, let's say if this is a knot, a curve can come like this, and the next curve can go like this. So there will be discontinuity here, as we cannot determine a single slope at this point. So one way to overcome this problem is by, say, aligning the tangents or slopes of these 2 curves at this point. Let's say this is the slope here, and this is the slope of this curve. So if we align both of them, then somehow we constrain them to be like this at this point. So we get a continuous smooth curve. So because we cannot impose this kind of a constraint on the gradient, what they have done in the paper is kind of introduce residual activation functions. If we take several basis functions, they're going to be like this, and they're going to be in different shapes. In order to ensure that they are combined in a smooth way, they have introduced residual activation functions in the paper. So that is what they have mentioned in the implementation details, which is that although KAN layer looks extremely simple, it's non-trivial to make it well optimizable. So one of the key tricks is to use residual activation functions. So they've included a basis function similar to residual connections, such that activation functions is the sum of the basis function along with the spline function. So you've got the spline function and you're adding up the basis function in order to form your residual activation function. And they've chosen silo, which is a standard activation function, for the basis function. So one of the other implementation tricks is that the initialization. So for each of the activation function, they've initialized the spline to be 0, and it's all initialized according to Xavier initialization, which has been used to initialize linear layers in multi-layer perceptrons. So it's nothing special basically. So we initialize the same way as we initialize the multi-layer perceptrons. Because we have B-splines, there's the introduction of the spline grids. So we haven't looked into spline grids. So let's look into that now. This example just depicts the simplest case where we just have 2 basis functions, but we can have multiple basis functions, or it can be more granular. For example, if we have more knots, we just have knots here, and we have 1, 2, 3, 4 basis functions. So that's how we change the granularity of the B-splines, or the number of B-splines that we use. And the more we have, the more complicated the function that we can represent using B-splines. So this idea of increasing the granularity of the B-splines is what is depicted in this figure. So we can see that we can go from a grid of size 5 to a grid of size 10. where we make them more dense and hence an extension of the grid. And this is equivalent to fine-tuning a normal neural network. So when it comes to a neural network, if you want to use it on your data set, we go ahead with fine-tuning it. But when it comes to KAN, we can actually do a grid extension and then train it on our data set in order to get the same effect as fine-tuning a neural network. So if we look at the grid extension, so in principle, spline can be made arbitrarily accurate to a target function, as a grid can be made arbitrarily fine-grained. And this good feature is inherited by KAN. By contrast, MLPs do not have the notion of fine-graining. Admittedly, increasing the width and depth of NLPs can lead to improvement in performance. That is what exactly we do. If you want to improve the performance of multi-layer perceptrons, we increase the depth of them or we increase the width of them, which has been shown by networks like white nets. So they reiterated saying that, for KANs, we can first train the KAN with fewer parameters and then extend it to a KAN with more parameters by simply making its spline grids finer. Now, this is one of the special features of KAN. So one of the disadvantages of using the splines is the computational complexity that it introduces. For example, let's take a network of depth L, which is a KAN network, and compare it with a MLP of same depth and same width. So if we take a KAN network, then the complexity becomes n squared LG plus K, or which is equivalent to n squared LG, where G is the grid intervals. In contrast, multi-layer perceptrons only have a complexity of n squared L, and so the complexity of multi-layer perceptrons is less compared to the computational complexity of KANs. But how does KAN defend this? So they have given this plot which says that the loss of KANs decreases quite fast compared to the loss of multi-layer perceptrons. Similarly, when it comes to the number of parameters, we could see that KANs have a very steep curve, indicating that the number of parameters you need for multi-layer perceptrons is quite high, and you can achieve the same performance with very less number of parameters with KANs. So that's the defense against the computational complexity. So the next bottleneck with KANs is interpretability. And what does it mean by that? When it comes to KANs, we actually have to choose the shape of the KAN that best matches the structure of the data. For toy problems, where we exactly know the equation that governs the data, it's quite simple. But in real world, we actually don't have an idea of this equation. So what they're suggesting in this paper is to start with a large enough KAN and train it with sparsity, regularization followed by pruning. So let's have a look at the steps or the ideas that need to be followed in order to simplify the KAN network. So one is sparsification. The next one is visualization. The third one is pruning. Fourth one is symbolification. So let's have a look at each of these. The sparsification is very well known in machine learning literature. So for MLPs, we use L1 regularization because the weights are linear, but there are no linear weights when it comes to KANs. They are replaced by learnable activation functions. So what we now have to do is sparsify these activation functions themselves. So they say that L1 to be insufficient for sparsification of KANs. Instead, they use entropy regularization. So the L1 norm on the activation function phi is defined as the average magnitude over its NP inputs. This is pretty much like taking a norm and then summing it up, similar to how we do an L1 norm, but that we are doing it on phi, which is the activation function, instead of the usual weights that we use in L1 normalization. So what they are additionally saying is that we also have to introduce a new term, which is to do with the entropy. Because it's not a normal thing to regularize on the activation functions, we need to introduce entropy as well in order to ensure that the training goes smooth. So the total regularization term then becomes the sum of the entropy term and the sparsification L1 norm on the activation function along with the prediction loss. So the second technique for simplification they're proposing is visualization. So what they're saying with visualization is that we can visualize a KAN to get a sense of the magnitudes. If we, for example, take the tan h activation function, the functions with small magnitude appear faded and to allow us to focus more on the important ones. But they haven't shown any visualization in any of the figures. So I have no clue what they're talking about when it comes to visualization. The next technique is pruning. So after training with sparsification penalty, we may also want to prune the network to a smaller subnetwork. Obviously, we need to use a threshold here in order to say that, okay, these nodes are below this threshold, and so we are ignoring them. And then we'll be making use of rest of the nodes which have a threshold higher than this. And for that, they're computing the input and output thresholds using this formula, and they're only considering nodes to be important if both incoming and outgoing scores are greater than this threshold. Next comes symbolification. So symbolification is when we actually suspect that there is some activation function that we can define, which is a standard activation function, or standard function like cos or sine or log or exponent. So they can provide an interface to set them to a specified symbolic form. So they provided this interface called fixed symbolic, and we can provide the function which is L, and then we could say that we want to use this symbolic function for this node, and it straight away sets this symbolic function. In order to do that, they obtain pre-activations and post-activations for some set of samples, and then they fit affine parameters ABCD. Basically, we have to calculate this parameters ABCD in order to use the symbolic function. So on top of these simplification techniques, they have also provided additional tools that allow us to apply more fine-grained control of the CANs, and that's in the appendix. I'm not going to go into the details because this by itself looks plenty to me. So this figure gives an overview of the simplification process. So you take a large network and then you first train with sparsification. You can see that sparsification leads to certain edges being connected, but certain ones not being connected. We prune them where the nodes that we want to prune are grayed out, and so we throw away those nodes. The next step is symbolification, where you try out sine, and then you try out squared, and then you try out exponent, and then you finally train with these affine parameters, and then you arrive at your network that's been simplified. So using the steps that we just saw, they trained KAN networks for 5 toy problems where we have different equations that are mentioned here. So in all 5 cases, the results confirm the same things. One is that MLP scales slowly compared to CANs, and MLPs plateau quickly. What that means is that this dark blue curve is the KAN, and we can see that it requires very less number of parameters in the first place. So what we achieve with less parameters, we need a lot more parameters when it comes to MLP. And the next thing is that the MLPs really have to scale, which means that we need to increase the depth of the network, or we need to increase the width of the network in order to achieve what we can achieve with the KAN. And this applies for all of these toy examples, 1, 2, 3, 4, 5 equations that we train for. So there are a couple of other experiments they have done. One is to do with the partial differential equations. They try to find out how the CANs and MLPs do when it comes to solving partial differential equations. As we have been seeing, the first thing that we'll notice is that CANs converge very easily, and we could see that the loss decreases quite fast compared to multi-layer perceptrons. The same applies for the number of parameters. So the KAN is indicated with this orange line, the green line, and the blue line. We can see that the number of parameters required decreases quite steeply for any given problem, indicating that we just need a small KAN network compared to a large multi-layer perceptron. And the other thing that's quite impressive with KAN is the continuous learning or continual learning problem. One of the problems that's persistent with multi-layer perceptrons is the catastrophic forgetting. So if we take a data set where we have these Gaussians that are in sequence, so we can see that in a sequence of 5 Gaussians that are passed one after the other, but the performance of KAN seems to be that of remembering whatever that happened in the past. But when it comes to multi-layer perceptrons, it seems to forget the previous phases in the data indicating that it's going through catastrophic forgetting, but that's not the case with the KAN networks, which is quite impressive. So on top of these experiments, they have done quite a few experiments to show that KANs are interpretable. So they used supervised toy dataset and then unsupervised toy dataset, and they've also done experiments on mathematical applications such as knot theory, and they've got some experiments on the physics as well. So one is to do with the application to physics, which is Anderson localization, whatever that means. But they've done quite a few extensive experiments to show that KANs perform way better, or if not, compared to MLPs. So they've also given a comparison which shows that when we should choose to use KAN versus when we should choose to use MLPs. So when should I use KAN or MLP? So one is accuracy. If you know the compositional structure, then KANs are the best, or otherwise either is fine. And if it's a complicated function that you are trying to learn, then again, KAN is the best. And if you're doing continual learning, we just saw that it's very good at catastrophic forgetting. So obviously KAN is the best compared to MLPs, or they say that either is fine. And then next is interpretability. If the dimension of the problem is quite high, either is hard. So even with KANs, you need a computationally intensive network, and with MLPs, you also need a much deeper network. But if the dimension is low, then again, obviously KAN is a better choice. And the level of interpretability. So if it's a quantitative, then we go for KAN, otherwise either is fine. And in terms of efficiency, if you want very small modules, then you need to opt for KAN. Otherwise, you could go for either MLP or KAN. And if you want fast training, you'll have to go for MLP. This is a big red light actually. So the training time for MLPs seems to be much lower than the training time for KANs. That can be attributed to the recursion when it comes to B-splines. So that's one of the things that I suppose will be the future work. And I can't wait to see more papers and more work that come that improve the performance of KANs. But right now, I think I've pretty much summarized and compared KANs and MLPs, and I hope that is quite useful for you guys. I will see you in my next. Until then, take care.